So after dealing with the and types of compound inequalities, we want to move into the other main type that we're going to be working with, which is joining statements together with the word or. So we'll come back to the same similar sort of example that we had, but now the difference is that we've got the word or joining these. So I'm going to make the same truth table so that we consider the truth value of whether it's cold or not outside, whether it's snowing or not outside, and then we'll consider in those different combinations of cases whether it's then true that it's cold or snowing outside. So it might be cold and snowing, it might be cold but not snowing, it might be not cold but snow. Oh, I made a mistake there. That should have been a false. Okay, and then like that, true, and then false, false. Okay, so those are all the combinations of possibilities we can have with cold and snowiness. So now we just want to ask ourselves, is it true that it is cold or snowing when it is true that it's cold and that it's snowing? And the answer is yes, it's true that it's cold or snowing. So if it is cold, but it's not snowing, is it true that it's cold or snowing? And the answer is yes, it's true that it's cold or snowing. And then if it's not cold and it's snowing, is it true that it's cold or snowing? And the answer is yes, it's true that it's cold or snowing. And then if it's not cold and it's not snowing, is it true that it's cold or snowing? And there it's false. So you can see that we end up getting truth whenever there was at least one true existing among the conditions, right? So what that ultimately means is that in order for the joining of a bunch of or statements to be true, so in order for an or statement to be true, then at least one of the conditions must be true. So if you just have, 1 out of 79 different individual conditions true and they're all joined together with or, then I guess you make that whole or statement then true. So if we look at this more algebraically now, so we have a condition that says that x is less than -4, which graphically would look like this with an empty circle, and then we have x is equal to or greater than 2, which would have a filled-in circle like that, joined together with the word or. Okay, now with an or, we don't need the blue and the red necessarily to happen together at the same time. We don't need them to both be true. So this is totally fine. And so we can have different disjunct or different disjointed parts of our graph, and that's totally acceptable. And that's what this graph is going to look like. Okay. All right, so some examples of solving these sorts of inequalities and graphing them. So it says to solve each inequality in the graph, same thing as what we were doing with the ands just previously. You can solve each of these simple inequalities separately when they're solved with ors. So here you can just multiply by 7/2, the reciprocal, to give you just 1n. So we got to multiply this by 7/2, so you can put that over 1. And then that's going to give you -28 over 2 on that side. Notice that we did multiply by a positive, so we don't have to flip that inequality symbol. This just simplifies down to n is less than or equal to -14. Then we go to the other one. I guess we can subtract 4. That's going to give you 0.5n is greater than or equal to 6. And then divide by half. So think, right? 6 divided by half. How many halves goes into 6? There should be 12 of them, right? So we end up getting that n is greater than or equal to 12. We didn't have to flip any inequality symbols there either because we didn't divide or multiply by a negative on both sides. So we end up getting this. You want to make sure that you write the word or. You have to write this out. And so this is what we get as the solution. And then if we're going to graph this solution set, -14 is the smaller of the numbers. You've got 12. So you've got n is going to be less than or equal to, so that, and then n could be equal to or greater than 12, and then that's the graph of your solution set for that or inequality. Great. So by the way, the only way you can ever write out an or inequality is you can only write a simple inequality and then another simple inequality with the word or. So you always have to have the word or. So if I go back to where we were dealing with the and inequalities, sometimes and inequalities we're going to write like that, where you can kind of join stuff together, but that's only when you have an and. Now, when you have ands, you can write the word and if you want. But yeah, there's no like abbreviated way that we can like join ors together. The only way is you have to like write the word or with these. Okay, so in solving these separate individual inequalities, then I'll have to divide. We're dividing by a negative there, so that means you're going to get the inequality symbol to flip direction there. That's going to go in 4.5 times. That becomes a positive 4.5 because it was a negative divided by a negative there. And then, so with this one, I guess we can distribute the half. That's fine. So 7k minus 4 is greater than 10. Add 4 to both sides. Divide by 7. K is greater than 2. So yeah, I guess I'll kind of move that over there so it's a little closer. So we end up getting that right there. So 4.5 is there, and k has to be equal to or less than it. And then 2 is smaller, but we're supposed to be above it, so it's going to be an open circle in there. So if this is an OR, right, and we need just at least one condition to be true, we'll at least get one of the conditions to be true there, as well as in that region, as well as in that region. So like, no matter where on the number line, we're always going to have a number that's going to satisfy either this inequality or this inequality. So I guess a better way to draw this out would be to just do this, and it's really the solutions are all real numbers, right? So another way to write that k is less than or equal to 4.5 or k is greater than 2, it's the same as all real numbers. So all real numbers satisfy that or component inequality. Cool. All right, with this one, quickly kind of solving, add 7, we get this, and then we got to divide by a negative, so the inequality symbol is going to change directions, you get there, and then I'm just going to get the v variable to the other side, so it's going to be v is less than negative 22, and then with the other one, we're going to get 18 minus 6v once we distribute. We're going to subtract the 18, which is going to give you 78, and then divide by the negative 6, so that's going to give you this inequality symbol is going to flip because you divided by a negative, and you get negative 13. Okay, so join those together with the word or, so we get that solution right there. So if I graph the first one, negative 22, we want to be just strictly underneath it. And then negative 13 is a bigger number than negative 22, so we'll put it more to the right, put a closed circle, but then we're going to go underneath it. So you can see that they both point towards the same direction, but because it's a word or, we kind of have a looser restrictions. We only need at least one condition to be true. So we're going to get at least one condition, actually both, to be true in that region, and just one of the conditions to be true. So really, for this OR statement to be true, really it can just be from negative 13 and below. So I mean, I'll still include negative 22 there, but really all of those numbers, they're going to be the solution. So really, this is the same as just saying all numbers that are less than or equal to negative 13 is ultimately going to make that OR component inequality be true. And then one last final example with ORs here. So if I solve the left-hand one, we're going to subtract 6. Be careful. It's negative 12. And then divide by 3. We're not dividing by a negative. We're dividing by a positive 3. So the inequality symbol stays. And then the other one, it's not so nice to distribute negative 1/3. So you can, since negative 1/3 is just timesing with the quantity 7x plus 10, you can just multiply by the reciprocal of negative 3 to turn it into a positive 1 times the 7x plus 10. And then you can just multiply that by negative 3. It avoids a lot of fraction sort of stuff. You get negative 18. Now I made a mistake right there because we multiplied by a negative 3 on both sides, and I didn't change the inequality symbol. So let's change that and do that the right way this time. Okay, so now we'll subtract 10, which is going to give us negative 28. Divide by 7. The inequality symbol does not flip because we divided by a positive. That gives us that. Okay, so we get x is greater than negative 4 or x is less than negative 4. So if this is where negative 4 is, this is saying that x has to be greater than negative 4, so empty circle. And this is saying that x is going to be less than negative 4, so empty circle. So it looks like the solutions that satisfies this compound inequality is pretty much every real number except negative 4.